Briefly, we talked about the acids, bases, and the definitions. Just a quick recap of that one. Electrolytes, we know, conduct electricity in aqueous medium, and acid, bases, and salts are actually electrolytes because in aqueous medium they dissociate. So I will be using the word dissociation and ionization. In case of electrolytes, it is almost same thing, except when we talk about in redox reaction, the definition is slightly different. But here dissociation and ionization is same thing. The strong electrolytes are completely dissociated. So we talked about, for example, NaCl, CaCl2. So these are the examples I have included. If you remember which are the strong electrolytes. A few more examples, acids and bases we will be talking about later. NaCl is a salt. A strong electrolyte means it will almost get dissociated in sodium and chloride ions. So at the equilibrium, basically, it will not be actually equilibrium because NaCl will be negligible. Almost 100% it will be ions only. Similarly for CaCl2, calcium chloride and sodium hydroxide. Calcium chloride again salt, sodium hydroxide is base. In weak electrolytes, there is equilibrium. So that's why weak acid, weak base. So most of our discussion you will see later on will be towards weak acid and weak base. The reason is because strong electrolytes dissociate completely and there is hardly any equilibrium. For example, acetic acid, ammonium hydroxide, these are weak electrolytes. Now again, the electrolytes should not be very, very weak. Otherwise, no dissociation will take place. So this is just opposite of very strong electrolyte. In case of very strong electrolytes, the reactant is not present, almost negligible. In case of very, very weak electrolytes, if we are talking about, the product will not be present because weak electrolytes will not dissociate. So there will be hardly any products. So most of the electrolytes we will be talking about will be somewhere in between, along with, yes, very weak and very strong. And then I'll tell you what we need to do if two are present, which one we can neglect, which one we can't neglect, and how. Later on, we will be talking about that. So Arrhenius acid bases, Arrhenius said that acids give hydrogen and bases give hydroxyline. So Arrhenius says both are given, hydrogen also and hydroxyline also. So for example, hydrogen halides, HCl, etc. A base molecule like MOH. So these are the bases. So here I talked about the acid. Acid is HX. Why HX in case of RNAs? Because there must be one hydrogen. Rest part can be anything. Rest part here it can be Cl, it can be Br, it can be another. For example, H2SO4. If I consider this can be HSO4 minus the X part. But there must be one hydrogen. So that's why one hydrogen has been written separately apart from X. Similarly, MOH, where there is one OH which gets dissociated. According to Arrhenius, there will be at least one OH which will be given by the base. So that's why written in this fashion. For example, NaOH, it will give you OH minus. So of this form, MOH will give you M plus. M plus can be anything, as I have already told you, and OH minus is given. Bronsted-Lowry, they just changed that. This is the same as the Arrhenius, that it gives a proton, that is H plus, but base is which accepts proton. That was the only change. And whatever we got, we called that conjugate base or conjugate acid. So if we are talking about acid, for example, HX, and it donated protons, so whatever is remaining, that is called conjugate base. Okay, just a So for example, reaction of aqueous ammonia and water, basically they produce ammonium ion and hydroxyl ion. So hydroxyl ion is given. So that's why how we will consider that which one is base, which one is acid. H2O gives hydrogen and gets converted into OH minus. It means this is acid because it gives hydrogen. It has lost hydrogen and has converted to OH minus. But when it loses the hydrogen, whatever is remaining, that part is known as conjugate base. Why that is base? Because if it accepts hydrogen, it will again get converted to acid. And that is the definition by Bronsted-Lowry of base, that bases accept hydrogen. So if this OH minus accepts H plus, it will again produce acid. So it is conjugate base. Why? Because it will again produce acid if it accepts hydrogen. Similarly, NH3 to NH4, it has accepted proton and got converted to NH4 plus. So that's why it is base. And whatever is produced is conjugate acid. Why it is conjugate acid? Because it can lose electron, lose proton. And after losing proton, it can again get converted to NH3. So it can lose proton, it means it is acid. But because it has been produced by this base, that's why it is conjugate acid of NH3. So try to understand this diagram. Write it down if you want to, and then I'll move forward. Base will produce conjugate acid, acid will produce conjugate base. But if you reverse this reaction, okay, for example, you write it NH4 plus OH minus, give you NH3 plus H2. In this case, this is acid, this is base, this is conjugate base, this is conjugate acid. Why? Because now it loses proton and produces NH3. So when anything loses proton, it is acid. Whatever is being produced, that is conjugate base in this case. Why this is base? Because it accepts hydrogen and produces H2O. Any species which accepts hydrogen is base, and the produced one after accepting hydrogen proton is conjugate acid. So those species which were acid, they are still acid here in this reaction also, but only conjugate word got interchanged. Conjugate word, why in this case? Because normally we use conjugate word at the product side. It means in general what we will be referring to, and in in future also I will be calling like that. I will be saying that NH4 plus is conjugate acid of NH3. And at the same time, I will be saying that NH3 is conjugated base of ammonium ion. And the reason is because there is only one difference of one proton. So the rule is conjugate acid base pair will have only the difference of one proton. If it can lose proton, it will be acid. If it can gain proton, it will be base. And both will be conjugate of one another. So if you have understood this concept, okay, then you can answer the questions here. What will be the conjugate bases for the following Bronsted acids? Tell me for HF. Hydrogen fluoride, what will be the conjugate base? Karan, excellent. Ashish, good. Divya, good. Arohi, the trick is that there will be only the difference of one H plus. Arohi, okay. Only the first one. I am not asking for the second one. Okay. Yes, Preeta, correct. Nothing else. So the best way to find out conjugate acid base pair will be only H will be different. That's it. So HF, if it is acid, it can lose one proton. So if it can lose one proton, after losing one proton, it will be like H plus and F minus, means this one will be the conjugate base. So if HF loses one proton, it will be converted to F minus. Now tell me of second one. Yes, Karan, Ashi, Rita, correct. Second one, H2SO4 is acid. What will be its conjugate base? Arohi, correct. So you got the idea, good. H2SO4, if it loses one proton only, Shivangi, okay, Devansh, Armina, correct. So there will be just one proton less, means one hydrogen less. Now, because it has lost one hydrogen, it will gain one minus charge. Okay. So don't forget to write the minus charge, Divya. Otherwise, your answer is correct. HSO4 minus. HCO3 minus. Shivangi, Ashi, correct. Good. Tuhina, good. Arohi, good. Divya, you have to consider the charge. Once it loses H plus, it should gain one more negative charge. Devansh, correct. Armina, correct. Rita, correct. Good. Shashwat, yes. Divya, don't forget to mention the charge because it is HCO3 minus. If it loses one proton, remember both left hand side and right hand side should be charged balanced. After losing one proton, it will be CO3 2 minus. Now here you have -1 charge. Here you have +1 -2, that is -1 charge. So conjugate base will be CO3 2 minus. Yes, Vanna, correct. Karan, yes. Next question. Now write the conjugate acid for these ones. First tell me for NH2 minus, what will be the conjugate acid? Definition is bases are those ones which accept proton, Bronsted bases. And when they accept proton, after that, whatever is produced, that is conjugate acid. Yes, Prita, got it. Just the definition. Write the reaction. Add H plus. That's it. These are Bronsted bases. If these are bases, as per Bronsted definition of bases, these will accept proton. When they accept the proton, it will be NH3. And here you have zero charge, -1 +1 on left hand side. On right hand side, you have zero charge. Okay. So these are bases. You are asked to find the conjugate acid, means conjugate acid which is produced on right hand side, product side. And bases are those ones which accept protons. Now tell me answer of the second one. Okay, good. Shivangi, Arohi, Tuhina, Devansh, you got the idea it means? Prita, very good. So because these are bases, when it gets one more proton, it will be NH4 plus. Yes, Ashi, correct. NH3 plus H plus and H4. But there are 0 and +1, that is +1 to overall charge. Here also there will be +1. Now tell me the answer of third one, HCOO minus. Shivangi, good. Preeta, Devansh, Ashi, good. Arohi, Shashwat, good. However, you have to write it differently, okay? The answer is correct, okay? You will get the marks. Yes, Ashi, that's why I said you have to write it like that. HCOO minus, when it gets H plus, it will be HCOOH, which is formic acid. Yes, Armina, Vanna, Tuhina, correct. You might have done in previous classes that it is actually present in the antisting. Okay, formic acid, which creates irritation on skin. So it is formic acid. Okay, next question. The species H2O, HCO3 minus, these can act both as Bronsted acids and bases. For each case, give the corresponding conjugate acid and conjugate base. It means when you are talking about conjugate acid, this species is working as base. Only if H2O is acting as base, you will get conjugate acid. Okay. And if it is working as conjugate base, the definition is it should accept the proton. When it accepts the proton, it produces hydronium ion. Yes, correct, Ashi. So this one is hydronium ion. This is known as hydronium ion. And the existence of hydrogen ion, okay, is not stable. H plus does not exist in water. In water, actually, we have hydronium ion. The H plus exists as H3O plus because it combines with H2O molecule and then it becomes stable after hydration. So remember, H plus does not exist. It is just for reactions. So in many reactions, instead of writing H plus, we will be writing H3O plus. Both are considered as same. There is no difference when we write H plus and H3O plus. Remember. So in ionic equilibrium, most of the times we will be talking about H3O plus. The reason is that H plus exists as hydronium ion. Now, if it you need to find conjugate base of H2O, it means at this time H2O is acting as acid. Only then you will get a conjugate base. And what is the definition of conjugate base? That it will accept the, I think in previous case I erased. I think that was opposite. Just let me check. Okay. So I'm considering that again. In first case, we need conjugate acid. So I'm erasing everything. H2O is here, which gives us conjugate acid. So if I need conjugate acid, it has to act as base. Okay. And the definition of base is that it attains H plus. And if it gains H plus, it is H3O plus. I think I had written the same thing probably. Now the second part, H2O. It gives you conjugate base. If it is acting as, you need conjugate base, it means it is acting as acid. And if it is acting as acid, it means it has to donate H plus. So H plus you will remove from it. And whatever is remaining is actually conjugate base. Yes, one Shivangi. She correct. So in this case, acid will donate H plus and will give you conjugate base. So in first case, answer will be H3O plus and OH minus. And remember, there will be the difference of only one H plus. That's it. So if you consider H2O and H3O plus, there's difference of one H plus. If you consider H2O and OH minus, there's difference of just one H. So in this case, the answer will be H3O plus and OH minus. Now tell me the answer of second one, HCO3 minus. So if a species is H3, HCO3 minus, first tell me conjugate acid, then base. Yes, Shivangi, Ashi, Aruhi, Shashwat, Nita. Correct. Aruhi, Shashwat, also tell me the conjugate base. Yes, Shivangi. One correct. Okay. So basically, the rule you need to memorize so that you are not confused. Yeah. The rule is simple. What Louis said. So according to that, whenever you get such questions, just write in rough somewhere conjugate acid that one more H plus. Conjugate acid will have one H plus more. Conjugate base will have one OH minus less. Sorry, one H plus less. And you will get the answers very easily. HCO3 minus means H2CO3. One H less, CO3. Then next HSO4 minus, add one H, H2SO4. Remove one H, SO4, 2 minus. Then you have NH3, add one H plus, remove one H plus. And those are the answers. Good. The answer I'm seeing, it means you have understood the concept. Very good. Now Lewis is based on the electrons. So Lewis acid and bases, as we talked about last time, Lewis further generalized it in the form of electrons because electrons are anyway there in all the species. H might not be there, OH might not be there, but there is no species which doesn't have electrons. So Lewis said that acid is an electron pair acceptor. And remember the keyword here, not just electron acceptor, electron pair acceptor. And base is an electron pair donor. So any species which tries to complete the octet by accepting the electrons, okay, means which tries to form the bond by accepting the electrons, that will be acid. Any species which will give the electrons pairs to form the bond will be base. Now, as far as bases are concerned, there is not much difference between Bronsted, Lowry, and Lewis. Almost same thing. There is not much difference. We don't have many bases where we can differentiate Bronsted, Lowry, and Lewis. However, in case of acids, there are many acids which cannot be explained on the basis of Arrhenius or Bronsted, Lowry, but can be explained on the basis of Lewis theory. In Lewis concept, many acids do not have proton. However, for Arrhenius and Bronsted, Lowry, the definition is same for both for acids. Yeah, that is they can donate proton. A typical example is, as I told you in the previous class also, BF3. BF3 is an acid, but we cannot prove it is acid on the basis of Arrhenius or Bronsted, Lowry because it does not have hydrogen, so it can't donate hydrogen proton. But on the basis of Lewis theory, that it is electron pair acceptor. On that basis, we can explain it as acid because when BF3 combines with ammonia, nitrogen has one electron pair, lone electron pair. So it donates that electron pair to boron, and then coordinate bond is formed. Coordinate bond means it is a covalent bond, but the electrons are provided by one species. So acidic nature of BF3 is explained on the basis of Lewis theory, not Arrhenius or Bronsted-Lowry theory. Now classify the following species into Lewis acid and Lewis bases and show how these act as such. OH minus. OH minus, normally we write OH minus, here it is written as HO minus. The reason is because oxygen has the electrons. Hydrogen does not have any extra electrons. So if I see oxygen and it is just minus, it means there are 7 electrons here. That's why there is one negative charge. 6 are of oxygen, and the one which is there with hydrogen here, the total 7. However, oxygen has only 6. So it means there is one extra electron it has gained from someone else. So that's why negative charge. Now, when it combines with H plus, I am talking about when it can form the water molecule. This H plus does not have any electrons. It means both the electrons are provided by oxygen. And then HOH bond is formed. On left hand side, we have zero charge. On right hand side also, we have zero charge. Left hand side +1 -1, zero charge. Here also zero. So because here OH minus donated electrons, that's why it is a base. Because the definition is base as an electron pair donor. So if it can donate an electron pair to form the bond, that's why it is a base, Lewis base. Lewis base. So that's why we are classifying these in Lewis acid or Lewis base. If there is anything you don't get, just let me know, okay? Electron pair donated. So you don't need to show everything, right? Because normally you will get this question in 2 marks. Means every part is of 0.5 marks. So you just need to write one line. Hydroxyline is a Lewis base as it can donate an electron lone pair. Remember that you have to write the pair. Next, fluoride. Again, it will act as Lewis base as it can donate any one of its 4 electrons lone pairs. So fluorine minus means it has 8 electrons. Fluorine normally has 7 valence electrons, but this minus charge means it has gained 1 more electron. There are 8 electrons. So if there are 8 electrons, means there are 4 lone pairs, and it can donate any one pair of these. Again, it is Lewis base. Both of these are Lewis base. Now come to H plus. H plus does not have any electrons. Yes, Shivangi. It means, as we have seen in case of HOH, that if it combines with OH minus, it will gain two electrons from H minus. Yes, Sashi. So it means it will be Lewis acid because it accepts a lone pair of electrons. And that is the definition of Lewis acid, electron pair acceptor. Yes, Divya, it gains electron pair. So it will be Lewis acid. Now BCl3. BCl3 case is similar to BF3. Exactly same. Yes, Sashi. Boron has 6 electrons now. B, Cl, Cl, Cl. Similar to BF3. So because there are 6 electrons, it will try to complete its octet. Similarly, NH3, these 2 electrons, it will accept. And as in case of BF3, similarly here it will gain the electron pair. Because it gains electron pair, it is Lewis acid. Accepted electron pair. So Lewis acid. Next, ionization of acids and bases. Arrhenius concept of acid and bases becomes useful in case of ionization of acids and bases, as mostly ionizations in chemical and biological systems occur in aqueous medium. So why, if you are asked, however, rarely this question is asked, but even if it is asked that why Arrhenius concept is applicable in dissociation of acid and bases, mostly it is because most of the biological and chemical reactions happen in aqueous medium. So proton will be available anyway. Following acids are termed strong. I'm going to give you examples and you have to memorize these. Yeah, strong acids, strong bases. Because they are almost completely dissociated into their constituent ions in aqueous medium, thereby acting as proton donor. Actually, very good proton donor because these are strong acids. All of these you have to write and memorize. Perchloric acid, HClO4, it will give you H plus ClO4 minus. You don't need to write H plus ClO4 minus. That is just to confirm that we are talking about Arrhenius concept. Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, and the last one, sulfuric acid. Why it is important to remember? Because sometimes in questions, you won't be given that these are strong or weak electrolytes or acids or bases. Based on whether these are or strong acid or strong base, weak acid or weak base, your answer will change. So in few questions, if you don't know, then you won't be able to get the right answer. Amine molecules are those are basically the organic compounds which have organic chain, for example, CH3, CH2, CH2, and then one NH2. So NH2 group is amine group. We will be talking about it in organic chemistry. So for example, this is propylamine. So I hope you have understood the strong acids. Now, strong bases. Strong bases are those ones which are completely dissociated, similar to strong acids. Strong acids are almost completely dissociated. Almost completely dissociated means when they are dissolved in water, for example, there will hardly be any acid, negligible acid, because most of it will get converted to H plus and ClO4 minus, for example. Here H plus Cl minus, here H plus NO3 minus, H plus HCl4 minus. So almost 100% products will be there. Similarly, here bases. These are so strong bases that if they are dissolved in water, they will get almost completely dissociated. Means Li plus plus OH minus. All these. And you can see that these are as per the Arrhenius concept. All have OH, so they can donate to H. So when they are dissolved, hardly any amount of the compound will be there, rather almost 100% ions will be there. So write down lithium hydroxide, sodium hydroxide, potassium hydroxide, cesium hydroxide, and barium hydroxide. So hydroxides of alkali metals and alkaline earth metals are normally strong bases. Alternatively, the strength of an acid or base may also be gauged in terms of Bronsted-Lowry concept of acid and bases. So this is something I explained for RNAs. For Bronsted-Lowry, a strong acid means good proton donor. It is applicable for RNAs as well. A strong base is good proton acceptor, means how easily it can donate or accept the proton. If it can accept very easily, it means it is a strong base. If it can donate very easily, it means it is strong acid. And that is common sense. If it can't donate H plus easily, so H plus will not be produced. It means reaction will not proceed much. It means it is not a strong acid. Consider the acid-base dissociation equilibrium of a weak acid. Now, remember when we are talking about equilibrium, normally we will be talking about weak acid and weak base because these will attain equilibrium. Strong acids or strong bases will get dissociated completely, ionized completely. But having said that, there might be a combination of both, and we will be doing numericals later on where we will decide how to calculate the concentration. Okay? So those cases will be different from this one. Here we have an acid. H is proton, A is anion, anionic part. Okay. When it reacts with H2O, because it is acid, H2O will be acting as base. Acid will not be reacting with acid. Acid will react with a base. And you know that in this case, as per Bronsted-Lowry, because we are talking about Bronsted-Lowry, acid, sorry, when donates a proton, gives you conjugate base. And base, when accepts a proton, gives you conjugate acid. So the equilibrium moves in the direction of formation of weaker acid and weaker base. And this is important to know because the stronger acid donates a proton to the stronger base. Why? Try to from this equation try to understand. This is acid. Okay? And when it donates a proton, it produces a base. If I say that this is a strong acid, it means it can lose proton very easily. Okay, clear? Now suppose this also, suppose, okay, I'm just writing suppose, that's why. Suppose conjugate base is also strong. In that case, it will accept H plus very easily and will get converted to acid because that is the definition of a base. It accepts H plus and gets converted to conjugate acid. So if this one is strong, it will not remain as it is, rather it will get the H plus very easily and will get converted to acid again. And we already know that the acid is strong, means it is getting dissociated completely. That is only possible if the conjugate base is weak. It means otherwise there will be reverse reaction. So conjugate acid or conjugate base, if we are talking about strong acid and strong base on the left hand side reactant, then the conjugate acid and conjugate base will be weaker. Otherwise, there will be reverse reaction. So that's what is written here. Equilibrium moves in the direction of formation of weaker acid and weaker base because the stronger acid donates a proton to stronger base. That's why it is written here. Both can't be strong. Strong cannot produce strong. Otherwise, the reaction will not be there. Forward and backward, both reactions will try to attain equilibrium, but because it is strong, it gets dissociated completely. If it gets dissociated completely, the equilibrium has to be towards the product side. Means the concentration of products should be maximum and concentration of the acid here, for example, should be minimum because almost 100% got dissociated. So remember, a strong acid or base will produce weak acid, weak base or acid. Okay, I'll show the bases again. Okay, these are the bases. Different product will be formed. Okay, acid will produce conjugate base, base will produce conjugate acid. But whatever products are there, if we are using strong reactants, then products will be weaker. And this is because it means they're, if they are strong, the reactants are strong, it means almost 100% reaction is there. And it is possible only if backward reaction is not possible. It means the products are weaker. The backward reaction is not possible only if the products are weak. It follows that as a strong acid dissociates completely in water, the resulting base formed would be very weak. Strong acid or base will produce weak base or acid. Acid will produce base, base will produce acid. That is, strong acids have very weak conjugate bases. Strong acids, as we have talked about, okay, perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic, nitric acid, sulfuric acid, all those, okay, will give conjugate base ions. These ones, because H plus will be removed from all of these, and these will be weak conjugate bases, much weaker than H2O. Okay, so these acids are much stronger, very strong as compared to H2O. Conjugate bases are much weaker than H2O. Similarly, a very strong base would give a very weak conjugate acid, that is vice versa. So if reactants are strong, the product will be weak. And vice versa also. If you have very weak reactants, the product will be strong. That's why the reaction is not happening in forward direction, because the strong product is getting dissociated and is producing the reactants actually. So forward reaction rate is much less than backward reaction rate. That's why weak reactants will produce strong products. So weak acid will produce a strong conjugate base. For example, NH2 minus. So this is basically amine group. Okay, it is known as amino group. O2 minus, H minus are very good proton acceptors and thus much stronger bases than H2O. So ultimately, what you need to remember that equilibrium will be like this. If on one side you have a strong electrolyte, on other side it will be weak electrolyte. Now the ionization constant of water and its ionic product we will be using because it is used, and that's why it is important to know. And how do we calculate the ionic product of H2O? H2O actually combines with H2. So one molecule of H2 combines with another molecule of H2O. Why? Because as I already told you, H plus does not have a standalone existence. H plus does not exist, highly unstable. When it loses an electron, it is highly unstable. So that's why it gets attached to H2O, that is hydronium ion. So in this case, if you see one molecule of H plus actually gains hydrogen and one loses. So the one which gives out is acid, the one which gains is base. That is the concept of Bronsted-Lowry. So acid gives you conjugate base and base gives you conjugate acid. From here, we can calculate the equilibrium constant, which will be hydronium ion concentration multiplied by hydroxyl ion concentration divided by H2 ion concentration. But we know that H2O is pure liquid. It means its concentration will be merged in equilibrium constant. And when it is merged, it is written as Kw. So Kw will be H3O plus OH minus. And this is very important relationship which we will be using later on. So you have to remember the equilibrium constant of water is given by hydronium ion concentration multiplied by OH ion concentration. As I said that H3O is actually proton, that is written as like this. We also write Kw equals to H ion concentration multiplied by OH ion concentration. So both formulas are same. So in few cases, you might get written as H plus concentration, OH minus concentration, or H3 ion concentration, OH minus. This is actually the ionization constant of water. It is actually equilibrium constant, but because ionization is happening, we call it ionization constant. Yes, this is how we are taking the acid, water as acid as well as base. So one molecule acts as acid, one part acts as acid, the other part acts as base. So water acts as both, and that's why it is called amphoteric. Okay? There are compounds which can act as acid and base, obviously with different compounds. So those are called amphoteric. Experimentally, the concentration of H plus or H3O minus, whatever you can call it, okay, has been calculated as 1 into 10 to the power minus 7 moles per liter. M means molarity, moles per liter at 25 degrees Celsius or 298 Kelvin. Clear? Now we see from this reaction that OH ion concentration and H3O ion concentration will be same because the ratio is 1 is to 1. So if this is X produced, this will also be produced X. So whatever is the concentration of H3O plus, the same concentration will be of OH minus. And if you have the same concentration, means H3O ion concentration is also 1 into 10 to the power minus 7. and OH minus concentration also 1 into 10 to the power minus 7. And you now know the formula that Kw is hydronium ion concentration multiplied by hydroxyl ion concentration. And when you multiply these two, you get 1 into 10 to the power minus 14. So Kw is always 10 to the power minus 14 at 298 Kelvin, or if temperature is not given in the question. If temperature is not given, you will always consider 10 to the power minus 14, Kw equals to 10 to the power minus 14. At any other temperature, it will be given. So don't bother about it. So the value of Kw is temperature dependent as it is an equilibrium constant. At any other temperature, it will be different. The density of pure water is 1000 gram per liter. It is 1 gram per milliliter or 1000 gram per liter. And its molar mass is 18 gram. We know that. From this one, we can calculate the concentration of the number of moles of H2O. Yes, the number of moles of H2O. Why I am calling it the concentration? Because I have already considered it as 1 liter. Therefore, the ratio of dissociated water to that of undissociated water can be given as 10 to the power minus 7 divided by 55.55. Remember why I have written it. If there is any confusion, let me know. Why I have written it as concentration. Let me explain if there is any confusion. This is because number of moles of water in 1 liter of it will be mass over molar mass. And in 1 liter from this density, there will be 1000 grams. So 1000 divided by molar mass 18, that is 55.55 moles. So molarity, that is concentration, will be number of moles divided by volume, number of moles 55.55, and volume is 1 liter. We have already taken one. That is 55.55 m. So from here we calculate the concentration of water H2O as 55.55. So the reaction, if I consider in simple terms, if I am not considering the hydronium ion, it is H plus plus OH minus in simple terms. Okay. If I consider hydronium ion, then I consider H2O plus H2O. Okay. In this case, I know the concentration of reactant, that is 55.55, and I know the concentration of H plus also 10 to the power minus 7, experimentally calculated. So I can calculate its ratio. It means H plus ion concentration is much less than the H2O ion concentration. It means H2O is very, very weak base or acid. It is approximately 1.8 into 10 to the power minus 9, approximately 2 into 10 power 9. Thus, equilibrium lies mainly towards undissociated water. The concentration of H plus is much less than concentration of H2O. It means H2O hardly got dissociated. So we can say that H2O, if it is acting as acid or base, is very weak acid or very weak base. So I'm going back to that equation here. It acts as acid and gives you a base. It acts as base, gives you an acid, but the concentration of these two concentrations will be equal, 1:1 ratio. Okay, so if it is 10 power minus 7, this will also be 10 power minus 7. And here you have 55.55, 55.55. So the concentration of reactants is much higher than the concentration of products. It means the equilibrium is mainly towards reactants. Hardly any dissociation is taking place. So H2O is acting as very weak acid and very weak base. If you are asked, you need to explain on this basis. We can distinguish acidic, neutral, and basic aqueous solutions by the relative value of H3O plus and OH minus. So this is something we are talking about any other electrolyte. In that electrolyte, if H ion concentration is greater than OH ion concentration, it is acidic because we have more H plus. If both are equal, it is neutral. If it is basic, then H3O plus ion concentration or H ion concentration will be less than OH. H plus corresponds to acid, OH corresponds to base. Any confusion, let me know. So in many cases, you will be asked whether it is acidic solution, whether it is basic solution or neutral solution, you need to use the concentration relationship. That's it.